Think about trucks and delivery vehicles moving around the city. They seem to drive endlessly doing their business. Have you ever wondered about how those companies are connected with one another? Let's talk about how complexities within a city can be modeled as a network. You are likely already familiar with many of the stakeholders in the context of urban freight, and you know that they all have different roles. There is a supplier or a shipper who produce and send the goods, and there are the receivers who ordered the products and the services. And then there are the carriers who actually transported the stuff. There are the administrators and the population at large. Those are the citizens for whom we want to make the city more livable. And remember, within each of these stakeholder classes, there are many individuals. In this particular video, we introduced the fascinating field of network theory. Unfortunately, we will not be able to get into the real interesting and deep stuff, but we hope to provide enough of an introduction so you can go on and help yourself further. Now, without worrying too much about the technicalities, you can appreciate that the relationships between all these stakeholders in urban freight and among different individuals in each group are pretty complex. And we still lack a universally agreed on definition for complexity, but I like the statement that appeared in the Journal of Science. All systems perceived to be complex, from the cell to the internet and from social to economic systems, consists of an extraordinarily large number of components that interact via intricate networks. So, in this part of the course, we are going to show you some basic examples of how we can model some of these complex interactions among urban freight stakeholders as a network, and the insights that one might actually gain from it. And no, not just because the science behind network theory is cool, although it is, but because it makes business sense too. Before we jump into the urban freight side of things, some basic terminology and concepts. A network or a graph is a collection of vertices and edges. Mathematically, we denote the graph as G, and it is a bold G because it is a set. It is a container of vertices and edges. The set of vertices is denoted by V and are also called nodes. The set of edges are denoted by E, and edges can also be called links or dyads. So, what is a node and what is an edge? And what do they represent? Well, the nice thing is that it can mean whatever you want it to mean. Let's look at a couple of examples. Consider two vertices, A and B. And let's be more concrete. A has some contract with B to supply goods. We would be able to model these two players in our example as the vertices and the contract as the edge. The contract is common, meaning that if A has a contract with B, then clearly B has a contract with A as well. It's reciprocal. In many realistic cases, you can quickly appreciate that things are a lot more intricate. The receiver B may have supply contracts with C and D too. And furthermore, B in turn has contracts in place to supply its customers, E, F, and G. So far, so good. But the roles of different players become very much blurred because it is quite plausible that these firms have more contracts amongst one another as well. You get the idea, right, of connecting vertices with edges. Now, that's not complex, I hear you argue. And you're right, but bear with me. We're still just introducing the basic concepts. We can define this graph here, G, as having a vertex set V that contains nodes A, B, C, D, all the way to vertex G. The edges are described as a pair of vertices. So we have AB, AC, and then BC. Note that we do not add edge BA, since it is already represented by vertex pair AB. We'll get back to that. All right, so we add each of the 10 edges as a node pair, And voila, we can describe a network of contracts graphically or using more formal notation. In this example, we used contracts, which is common. It implies common edges. That is, the edge AB is the same as BA. The direction does not matter. We call this graph undirected. But what if we're not interested in contracts, but rather actual products moving? Then this common assumption does not hold anymore. If A supplies B with goods, it does not mean that goods flow back from B to A, right? And this brings us to the idea of a directed graph. Let's say the edges now don't represent contracts, but rather physical goods being moved. We see that goods are shipped from A to B, but not from B back to A. While goods are shipped from A to C, there is also a reverse flow from C back to A. And we represent those as two separate edges in the graph, AC, CA. Again, it depends on what you want to model. If the direction of the edge is important, it is important that you consider a directed graph. Goods moving, vehicles traveling in a specific direction, financial transactions flowing, phone calls initiated, documents being forwarded. In such cases, their direction may indeed matter. The type of edges may also differ. Some might represent goods, some might represent financial transactions, others paperwork flowing, and so on. Also, the node types might differ. Some nodes may be classified as receivers, others as having some production capability. You get the idea. What we often do is to create the different types of networks on different layers, and then we connect those different layers with one another. In such a case, we refer to it as a multiplex network. But don't worry, that is already quite advanced and beyond the scope of our session here. Finally, something we are going to look at in more detail later is when edges or the vertices are weighted. So one approach might be to say that the more goods, let's say by volume, that is flowing from A to B, the higher the weight of that edge. The less the volume, the lower the weight. Conversely, you may use distance as the weight. So the closer that A to B is, the lower the weight. And when looking at the vertices, you may weigh them by their inventory carrying capacity, for example, or by their market capitalization. And as you might already be thinking, you can mix and match these graphs to study whatever the phenomena is that you are curious about. But be careful though. The fact that you can model a weighted, directed graph does not mean you should model it in that way. What is the right network type? That's a tough question. And that is only partly science and partly art, which comes from experience. So be guided by what the leading researchers are publishing in that field. In another video, I will talk about different ways in which the vertices are actually connected and why that makes studying graphs so interesting.